So let's resume where we finished. So hopefully today I can finish the proof of the factor theorem, but well, we'll see. We will check soon if we can do it. So let me restate the last lemma I stated. I proved it using mixing, but actually you don't need anything, any hypothesis for it. So I want to restate it in completely abstract terms, and then I go back to what we were doing. So it's a lemma that actually we already did, but let me do it again. So let T be a homeomorphism of a second countable metric space I don't think I need locally compact, so I need locally compact. Oh boy, I'm starting with this problem. Another application will be locally compact, so let me assume locally compact. Mu probability measure. Yeah, actually, if you want the measure to be nice, you need the space to be locally compact. If not, the support of the measure will have to be locally compact. If not, it's very hard to deal with this measure. So, so you want the regularity of the measure, essentially. And this will come from there. Anyway. So we have a homeo of a 700, blah, 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 blah. So let phi be, say, in L1 of mu be such that phi compose T equal to phi, mu almost everywhere. Then there exists a set R such that mu of R. So it's Mautner phenomena in a sense, such that if x and y belong to R and distance of f and x to f of x is t, t and y goes to 0, then phi of x equals to phi of y. Okay, so an invariant function is constant on stable manifolds. That's what it says. And this is true for every L1 function. So for continuous functions, it's really, well, for uniformly continuous function, it's really a triviality. For continuous functions, you have to be careful at infinity, essentially, because I'm not assuming compactness here. And the point is that it's true for L1 functions. Actually, it will be true for measurable functions, but it's not important for our situation. So we will want to use it for bounded functions, essentially. And that, and also you can always do the trick that we have seen, so observation, so that's really a completely useless hypothesis. Remember the trick. You just take a function u from R into interval 0, 1, measurable actually, diffio. Okay, and then you consider u compose phi. And then this automatically becomes any measurable function into a bounded function. And since u is a diffio, having this for u compose phi and having it for phi is the same. So, well. Okay. So proof is really straightforward. So take phi n in L1 mu actually, compactly supported continuous functions. Continuous such that phi n goes to phi, say in L1. Okay, so let now phi tilde n, and actually this is the same definition for every function, is the Birkhoff average, limit as n goes to infinity, 1 over n, sum from 0 to n minus 1 of phi n compose tk at x, and Birkhoff theorem plus the continuity, or uniform continuity actually, tells me that 1 there exists a set R naught, mu of R naught equals to 1, such that limit star exists for every x in R naught. Actually, let me restate this. So let R naught be the x such that star exists. And then Birkhoff tell me mu R naught equals to 1. That's Birkhoff. Exists for every n. So this is Birkhoff used countably many times. And second, if x and y belongs to R naught and distance from tkx to tky goes to 0, then actually even more, if x belongs to R naught, actually I just care about the other statement, but let's write the strong statement. If x is in there and the distance goes to 0, then y belongs to R naught and phi tilde nx naught, phi tilde x equals to phi tilde ny for every n. Okay, and that's just the continuity. So the uniform continuity. Now I just need the third, which is L1 convergence. Well, phi tilde n goes to phi tilde L1. That's also a consequence of Birkhoff-Ergodic theorem. And actually, for that matter, we could go do it with L2, which in which case will be a consequence of von Neumann theorem. And what we care is a consequence of 3, which is there exists ni going to infinity such that going to phi tilde almost everywhere. Because whenever you have convergence in measure, you have convergence almost everywhere. So we can go to the subsequence and forget about the original sequence and stay with the subsequence. So let R1 be such that if x is in R1, then phi tilde ni of x goes, and then we just put these together. So if x, y belongs to R naught intersected R1, of course we care R1 being full measure, then phi tilde x is limit and I going to infinity, and here we are assuming tkx to tky going to 0. Now, since the guys belong to R0 and the distance goes to 0, we have this equality, and belonging to R1, we got this equality, and then we are done. And if you call the asymptotic stable set of x this guy, then this is saying that the function which is constant along orbits is constant along stable manifolds, even though they are not manifolds, they are just a partition. Okay. And what we stated before, essentially, the assumption that was in the R0, okay, let me go back to what we did last time. So we had ij, we pick an s such that actually we pick two guys, and we want even a stronger version, which is what I stated, but still let me go back to what we did last time. So we take s just that, or t, just that ti minus tj is negative, and oops, 0, and ti naught minus tj naught negative. So I have contraction along the I naught g naught direction, and I have isometry. And then we take the measure mu bar ig sub p. This is the measure on R, which is the pullback onto R of this. And the two observations is, if you call this phi of p, we have that phi of a sub t of p is phi of p. So that was one of the observations we saw. So for the tilde is a different picture, but when we bring this back to the reals, this is just full invariance. We have used it actually also before in the measure rigidity. And the other property is that if y is h I naught g naught s of p, then we have that the distance of aty atx goes to 0 as t goes to infinity. And then if we apply the lemma before, we get the previous statement without any mixing assumption, without anything. So we have that then the value at p and the value at y will be the same. But it's even more, so I can do it more globally, not just for the I naught j naught, I just can do all the way. So okay, now comes, let me just do the proof in SL3, and maybe we discuss a little bit about larger SLN and more general situation. So we have our P invariant measure. So the P is this upper triangular guy, so the measure is invariant under all these directions. I call n minus these guys. Is this perpendicular guy. There will be a Q minus eventually in the proof, which if I don't gain, if Q were equal to P, Q minus is equal to N minus. Here in the next situation, Q will be equal to D, and minus will be just taking this group generated by these two guys. yet let's and the claim would be is that the conditional measure mu along Q minus is delta P almost everywhere. Mu almost everywhere. Mu bar. Well, without the bar, because if I put the bar, then I should put the delta 0. Okay, but it's the same. And the consequence of this is the consequence, even though it's not. So one half to the work, it should be almost an immediate consequence. So from the geometric point of view, it's really a completely direct corollary, but when you write the proof, you have to argue a little bit, is that the conditional along the G is the same as the conditional along the Q, P almost everywhere. Okay, so these are the statements, the two lemmas. So the lemma and the corollary that essentially will almost finish the normal subgroup theorem. Then we will discuss with a little bit more detail how from here we actually deduce that the factor is injective. So the pi function is injective. Okay, so let's see how to prove this lemma 1. And remember, Q minus is generated is equal to subgroup generated by all Hij not in Q. Okay, you look at all directions not in Q. If they are not in Q, then you put it in Q minus, you take a group generated by it, and it is what it is. And it's actually the whole point, and that's the point of parabolic groups, which are the groups containing P, that it has these complement groups, because they always have this sort of staircase type of picture, which in matter of symmetry tells you that this staircase is still a group down there. Now, for the proof of lemma 1, it is important to recognize this guy. I will try to write down who is this guy. Actually, this guy would do, this other guy also would do. But it's guys which are the closest to the cube possible. Because this satisfies certain property. So let me draw a 4-dimensional or a larger dimensional situation. And maybe let me first write down the definition of the I naught G naught I want to discuss, and then I draw the picture. So take I naught G naught. Sorry. Okay. So given a group Q bar inside Q minus, actually it has to be with the Lie algebra, so I want it. Okay. Just like it could be connected or closed and connected. Once it is closed and connected, is the exponential of its Lie algebra. So that's actually what I care. Okay. So given a group Q bar here, we define I naught J naught where no, I don't want this, right, because a subgroup is too general. So I want a very specific type of subgroup. I'm very sorry. Let's try again. So given a set of roots H ij, so it's some set of roots R with I, okay, I want them to be down, so I want the line to be larger than the column, I larger than J. Maybe let's emphasize that this is a subset of roots. We call it complete if the group generated by all these guys amounts to all the guys together, okay? Which essentially means that whenever I have two guys, the bracket also belongs to the same root. So then Hij bracket Hi prime G prime belongs to R. Okay, so this tells me that the R still satisfies this staircase type of assumption. So I'm not missing anyone. And you can always complete a set of roots to one such guy. You just keep adding the guys. Eventually, there is a funny dimension because you are always inside the G after all, but inside the N minus, so you have to finish at some point. Okay, now given such sets, a complete set of subset actually I could call them negative roots because of this property. So this is negative. We define I naught J naught, which is the upmost and rightmost entry, such that I is smaller, larger than I naught for every ij in R, and J is smaller than J naught for every Hij in R. Okay, so this definition actually can be done no matter what, essentially. But the assumptions we are making is in such a way that we are having a bunch of stars, say, which are the complement of this group generated by this R. And then, let's say this is the guy here. So I identify, let's say you have this guy as well. Then this is the I naught J naught, where I cannot go up more. And then I move to the left. I cannot go more to the left or to the right. Now the assumptions on the completeness tell me that all these guys also will belong to the complete set of roots. All the guys above and all the guys below. And I have actually this rectangle belonging to this set of roots. Okay. Now here maybe more people or not. That I have no clue what's happening down there. But I have all these rectangles. That's the assumption of completeness. And I'm detecting this guy. So what the importance of this is that there exists T in R to the n, sum of the Ti being equal to 0, T1 larger than T2 larger than Tn. So this is the condition that guarantees me that the lower triangular region is being contracted when I move along this T. And actually, I'm allowing the inequalities because I will require some inequality at some point. And I can choose Ti naught equals to Tj naught. So I want to freeze this direction. But then I want to keep all the other guys inequalities as much as possible. And Ti is larger than Tj unless, okay, now I is larger than j, so I, unless I'm in this place where once I have this equality, I need to have all the equalities in between because they are ordered. And then unless I'm in the place where I'm forced to have the equality, I still have the correct inequalities. So everything contracting, but the guys that are forced to be equal. Now, what are these guys which are forced to be equal? So certainly the I naught, j naught, but not any other ij will have I smaller or equal. So if it is strictly smaller, it's up, so I don't care about, these are stars. If it is equal, then the j has to be larger, which means I'm moving to this direction. So again, these are stars, so I don't care. So which means that of all the roots I care, belonging to this complete set, the I naught, j naught is 0, and all the others are negative. Okay? So by this choice,
You're taking the top right corner of the first rectangle, but there may be other rectangles as well.
there may be another guy down here that also would do the same job essentially.
You just take one.
I just take one. So it's one that will do actually what I want, and I will now say it explicitly. What I want is the following. So H yeah, I want that Ti naught equals to Tj naught, and Ti minus Tj is negative for every I in R Hij different from this Hij. So I want to be able to pick the T doing this, where there is one guy which is identified and all the others are negative. Who is the guy? Actually, I don't care. So this is the way, the simplest way to identify this guy, I naught, j naught, taking this top right entry. Another one that certainly would do will be taking the guy, I think, down here. But it's a matter of symmetries. Yeah, down there or down there, who knows? Anyway. So essentially, you essentially want to stay towards the border of this. Okay, why do I care about this? Because I want to apply the previous statement. So R hat I naught G naught, which is all the Hij's such that Ij all the h I said in R, such that h I naught g naught different from hij is a complete set of roots. Okay, so I'm not missing this guy. So the reason for that essentially is comes from the bracket assumption, and here is one important observation between the brackets. So you do hij bracket with hkl. This is 0 unless j equals to k. That's the first observation. And the second observation is that when you are doing the, okay, too many commas, I have to be careful. A JL, this guy is HIL. Okay, and finally, you see that the associated contraction is the Ti minus Tj plus Tj minus Tl. Now, it was complete before. If it were not complete now, it's because I have one bracket giving me the I naught G naught. But these entries give me negative plus negative. It cannot be 0. Okay, so that's the proof of completeness. So that's a dynamical proof of completeness. One can just do the completely numbers and do it. Okay, so then this guy is a group, generates a group, all these guys. So inside my group generated R, I have this group R hat, which is transversal to my I naught J naught direction. Okay, so I have in such a group R, which is inside the stable, I have this separation where I get one contracting direction, but I'm sorry, one isometric direction, the complement fully contracting. And that's what we prove in the lemma. When I have this structure, I have that this contracting direction is constant. This isometric direction is constant with respect to the contracting. Okay, so why I put R instead of just going with the Q minus is because I need to make some inductive argument to be going down, and I need to argue a little bit more. So, proof of lemma 1. So, assume mu tilde Q minus P is not atomic. Okay. Now, here's what I will do, but then I will write it in a more mathematical formal way. But what I'm going to do is I take the I naught J naught. I have this direction I naught J naught. I take the complementary direction R hat I naught J naught. And I know that the measure on this direction is atomic, because if it were not atomic, it will be inside Q. And I also know that these conditional measures are invariant for the points belonging here. So I know that all these conditional measures are all atomic, but not only are atomic, they have to lie. So it's being atomic is telling me that it is a graph, but the lemma we just proved tells me that this graph is constant. Okay? Which tells me essentially that this mu tilde Q minus P is equals to R I naught G naught P. This measure is exactly lying here. Okay, and then I have to start from here and continue. and continue with induction. So I lost one dimension. I have that this measure is not atomic, and then I continue. So instead of doing that and keep on putting dots, I will just call R the guy with minimal dimension. There may be more than one in principle. I just take one guy with minimal dimension where this is not true. Okay, where they have that this is different from delta. So let R be a complete set of roots, of negative roots, R inside Q minus, such that mu tilde R P is different from delta P, almost everywhere. Some ergodicity tells me that this is either a 0 or 1 set, so I don't care really about the positive measure versus 0 measure of minimal dimension. And I have to get to a contradiction, so I will get a contradiction of the minimal dimension of this guy. So, well, such guy exists because I could always take Q minus, and if someone is able to find something smaller, happy. If not, I still have Q minus to play. Now we do the argument, the one I just wrote, R hat I naught G naught associated to this R, then the claim is that this is true. And the proof is exactly what was stated in the previous lemma, in the first lemma we discussed today. So I'm using too many R's, so let me put a different name. Let D mu of D equals to 1 from the first lemma today. And then the claim is that D intersected the Q minus orbit of P is equal to D intersected with the R hat I naught J naught orbit of P. P almost everywhere. So that's essentially the claim. And this is exactly the same as this, because this is telling me that the complement of this guy inside the R orbit has 0 measure, just because of this intersection being equal. And D has full measure. And maybe move to the right. So why is this true? Let's do it here. Maybe I should assume something else in D. Second thing I'm assuming, so that was 1. Not that, sorry, is that. And the second thing I'm assuming on D is that if P belongs to D, then mu tilde I naught J naught P is delta P, which I can also assume. So once I have these two properties, then I have that if X or Q belongs to D and Q belongs to the Q minus, to the R orbit of P. Yeah, this should have been R, which at the end of the day will be Q minus as well, but let me go with R so far. So then I have to upgrade to Q minus. So take Q in this R orbit of P, then I can write Q as being the I naught G naught point of some Z, C in the R okay, let me write it correctly. So is H I naught G naught S times Z for some Z in R naught J naught hat. So what I'm just writing now here is the following. I have P, I have this two-dimensional picture. This is R orbit, this is R hat I J naught, this is Q, this is the I naught J naught direction it hits here. Okay? So this is just a fact about product of matrices. Okay, when I have this matrix, any matrix in this down triangular guy, I can write it as the composition of one matrix which has only one non-zero entry in this point, and a matrix that has this guy as a zero entry. And that's it. So this is the matrix which has this entry 0. This is the matrix which has this entry non-zero. So I'm writing this guy. Okay, now I essentially want to claim that this point actually has to belong here, into here. So that this Q cannot be outside, because Q is in D. So I know that the conditional measure here is 0. Now I'm having a slight problem with the fact that this guy is not being contracted toward this guy. This guy is going to contract it towards this point. I may need an improved lemma. We would have the improved lemma, but I didn't want to do it with the improved lemma. So bad. Something is not doing the job. Somehow I stated the lemma wrongly. Or I'm doing something which is wrong. So let me first go from the positive side. So what we wanted of the lemma is to say that if I have this conditional here, and I have this conditional here, and I do this movement, horizontal movement, then this conditional here has to move into this conditional here. Okay. Now, to be able to say that, I cannot do it at any pair of points I want. I have to do them on that the points belong to some set of full measure. Because I'm using ergodic theorems, Lucin's theorem, so I really need to restrict to some set of full measures. So I take P in this set of full measure, and now I'm taking Q in this set of full measure. Now these P and Q in principle don't lie in the same horizontal, because after all that's what I'm trying to show. Yet I want to show that still for these P and Q that are not in this same set of full measure, when I do this holonomy here, this measure match this measure. Okay, so that's what I still want to prove. And clearly this will imply that the Q has to be over this line, because when I do this movement, which is a very symmetric movement, P is moving into here.
Well, I could assume that Q is in this table.
Well, that's not, because I want to show this equality, and so one inclusion is obvious in principle. So because this set is inside this set, now I want to show that inclusion. So I only have that this guy is in the two-dimensional picture, and I want to show that actually it has to belong to the one-dimensional picture. So, and that for this, that's why I cannot assume that the Q is here. I really have to state the lemma so that Q belongs up there. So let's state the lemma, and then we prove the lemma. So I only stated it before for the stable. Now I will have to state it a little bit stronger than this stable. So let's restate it. The lemma will say exactly what we want here. Then we will see how general we can restate it to derive it from. But I have that there exists a set D, mu of D equals to 1, such that if P belongs to D, Q belongs to D, and Q is in this R hat I naught G naught of P, I'm sorry, in the R of P, then for the choice of I naught P naught we cared. And I slide it along the R hat I naught G naught. This is equal to mu tilde Q I naught G naught, equal up to a number, as always. Okay, so I'm just stating them exactly what I need. I take 2 points there, I do this movement, this holonomy. Okay, so here pi R hat I naught G naught goes from the W I naught G naught of P. I should put here a PQ into W I naught G naught of Q, and is defined by R hat of X is this W I naught G naught of Q intersected with this horizontal. Nice. R hat I naught G naught of X. And the proof will be pretty much very similar to what we did on Wednesday, actually, because I not claim fully ergodicity, so I have to still claim something, but...
So the verticals in this picture is the W I naught G naughts.
Exactly. Okay. So that's the lemma that we will have to prove. So we are going to prove it later today or Wednesday. And so now, assuming we have the lemma, then I have the inclusion needed there, and then I have the equality. So I have the P, the measure is delta at this P. I do holonomy, it cannot go outside, it has to go over the same line, which tells me this equality. Now this equality, since okay, what does this equality tells me? This equality tells me that this conditional measure for the R is the same as for the R hat, but then this guy is one dimension smaller, and it has to be non-atomic because this guy was non-atomic. So that's a contradiction. Okay, so good. We got this statement.
So for this improved lemma, we're going to have to do something more. It's not just like this regular Birkhoff argument.
It is a regular Birkhoff argument, actually. So it's simply that I will have to do it for P and Q. I need the fact that the Birkhoff average for P and the Birkhoff average for Q are the same. Once I know the Birkhoff average for P and for Q are the same, then I'm fine, which again, in this algebraic situation, I can go with easily because I take the T as always, freeze in this direction, move in that, contract in this direction, and I know it is ergodic. Then ergodic averages are the same everywhere at any given pair of points. If I argue the mixing, then the product will be ergodic, and then I can just argue with the product like we did in previous Friday, and I'm happy.
But then you didn't need the improved lemma if you're going to use rigidity.
Exactly. The point is that, so that's the way out. I'm just saying how to prove it to save the day. Okay? Now, this is true in much more general situation. You don't need much more than just Maudner phenomenon, essentially. And this is what is called, yeah, I forgot, I should have this said before. So all this we are discussing, this picture essentially is what is called the high entropy method. This plus yet another consequence of this that we will not need, but we could discuss later by Einsiedler-Katok. So actually they use this picture, but with one more, so this lemma, but then they do one extra game, which is a bracket. And then they spread the measure further. So we don't need to actually argue as hard as all they do because we always have ergodicity. So we have this ergodicity assumption that makes our life much simpler all the time. We have even mixing. So products are ergodic if we want. So it's really a very pleasant situation we are here. So in the more general situation that they face, you only have ergodicity of your total actions and not of the individual elements. And then, yeah, you really have to, you are picking a very specific element, which is this T doing this, this, and that, and you have to argue from there. So I will do it probably later, but not now. I have to think it over a little bit to see how we bypass this problem here. I have to remember how we do it. But, okay, for this subgroup theorem, where we have all the ergodicities we care, so this lemma essentially is done. And we hence have the lemma 1. Now we have to move to the corollary, where we have to prove that this G measure is actually in the Q. Okay, but for this, let me draw the picture again of what we know by now. And hopefully I can convince you that essentially this corollary is a corollary. And by the way, what we just proved is also a very important step, which is how to relate this equality to intersection of sets. Because we care about intersection of sets, and we just saw how these two guys are really related. So I still will do it again, but I will repeat essentially the picture we just did 2 seconds ago, now in this second framework. But now we have the two-dimensional G guy. I have the Q direction and the Q minus direction. And really think of this as being R2 foliation by Q by R horizontal, foliation by R vertical. The fact that these foliation do not commute is really not of significant importance in our picture. Now we have a measure mu GP, which first mu tilde GP, which is equivalent to mu tilde QQ if both are in the same G orbit. Okay. So if both measures are in the same G orbit, these measures are pretty much the same. That's one thing. Second, the measures are Q invariant. So mu tilde of let me write it in the correct way. Q bar is essentially the same as mu tilde P. Oh, too many Q's. Okay, let's call it X, this other guy, of QP. If Q belongs to Q. Okay, so that's the Q invariance of the measure mu tilde becomes this invariance here. Now the third thing is that the vertical measure, the Q minus measures, are all atomic. Yeah, this is atomic for almost everything. And once I know this, I want to claim that such a measure is the hard measure along this Q. Okay, let's see how should we convince ourselves of that. Okay, let me first state it with epsilon care, saying that there exists a set R, mu of R equals to 1, such that this is true whenever P and X belongs to R. And here we also require Q times P to belong to R. So because after all this mu tilde only makes sense on a set of full measure. So I need all these points to belong to this set of full measure. Okay, then we take R intersect this P orbit, and I have this set which has full measure along the P orbit. Second. Let's see if I can do it. I may fail, and then we try again. Let's take a point here in this set of full measure where all this is true. And assume that's not so. 2 points. Let's take P here, which is the origin of our picture, and then let's take another point Q, and let's assume it's not in the Q orbit, but belongs to R. Okay, and I can assume, although I should have said, but this is really not hard to claim, that Q minus times Q of P is the same as G of P, which means that something that was trivial before, here it requires epsilon more of work, but it still is true for almost every Q in R, that I can reach the Q in this way. Okay. Now, I have the Q orbit sushi here. And as I said, I want to claim that this is trivial. Okay, so what I want to claim now? So certainly I want to contradict this property here. So this point here is of crucial importance. Which means I want to be able to write the Q as well, the G as well the other form, Q minus of P. This allows me to define this guy where I move that way and then reach Q. But I still need sign point. Okay, now I remember what I wanted. Okay, now it's a little bit of Hopf argument first. So this Z may not belong to R. Okay? But I know that almost every point with respect to Lebesgue nearby here belongs to R. The same thing up here. And I know that this vertical foliation is a smooth foliation, which means it sends set of full measures here into sets of full measures here. Which means that if I take R intersected with this interval and R intersected with this interval, both are set of full measures here, and I can assume, restricted to a set of full measure, that it's ended here to here. So by moving a little bit the Q and hence moving a little bit the C, I can assume that actually C belongs to R. Which then implies I can switch from P to Z, because playing with P or playing with Z is no difference. I could have started with P. I have 2 points now in R, which belongs to the same vertical Q minus. But that's impossible, because that's exactly what it means, but I can restate it as R intersected Q minus of P is P for every P in R. So that's the way I want to restate this. And actually what we showed is, by the same token as we did this and we did this argument, is that R intersected GP is the same as R intersected QP for every P in R. Because if I take a Q here, lies outside there, then I move from the P to the C, and it lies there. Okay, so I prove the corollary, and not only prove the corollary, I prove what I really wanted out of the corollary, which is this property. Because this is the injectivity of the guy. So let's finish with the normals, with the factor theorem, which hence finish the normal subgroup theorem. And luckily this point was useless. So oh, 10 minutes. Okay, then let me, yeah. From time to time look at this, but that I think I don't see it. Okay, so let's stop then, and we do it on Wednesday. Okay, thanks. Yeah, you should stop. Okay, so I promised I was going to do something. I'm not going to do it, so probably I will do it at some point in the future. Maybe I will discuss in any event some related things, and probably we'll try to cover also these related things. But let me finish completely with this factor theorem that then gives us the normal subgroup theorem. So we have two things to do. I have to prove the lemma that I stated down here. I wave the hand, I show you more or less how you do it. I want to do especially one computation which is somewhat classical, and I want to have it in the blackboard. And also how is the end of the proof, that pretty much we went through. So the lemma was the following. So let me draw the picture of what the lemma was saying. So we have this direction is contracting, this direction is isometric. So this is some h I naught j naught. This is some family R hat where this I naught j naught was chosen in some maximal way so that it was pretty much up there, and all the remainder guys were negative while this guy is 0, so that I can choose Ti naught equals to Tg naught while Ti minus Tj be negative for all Hij in these other guys. So this is complementary. So this gives me this stable foliation here and this freezing guy up there. And we were in the middle of an induction. Well, actually, it was not an induction. This R I J naught, I naught J naught, was chosen. So it's a family of ij's. Actually, it's some R rather than I naught J naught. It's some family of ij's which is integrable. So we have this completeness property. So that the close with respect to taking brackets, which make it integrable. And and we assume that the conditional measure along this group generated by R was not atomic, and it was of minimal dimension. And what we are going to show is a contradiction that claims that actually the measure is just the conditional measure along this R is supported on this horizontal, and then contradicts the minimality of the dimension that was chosen. And we're going to use the fact that this guy, the condition along this vertical guy is atomic. Okay, so then what we need to show essentially is this product structure of the measure. So the lemma we have proved before was only stating that if I take 2 points typical on the same horizontal, then the measures has to match. But we need a little bit better than this. We need to be able to compare a point P here and a point Q here and still have this holonomy invariance. And that's what we are going to do, assuming the ergodicity that we have. Okay, so let T bar T be such that Ti naught equals to Tj naught, Ti minus Tj negative for every ij in R hat I naught G naught. Then there exists a set T mu of D equals to 1 such that if X, Y, or PQ belongs to D and Q is in R of P, so R of P meaning exactly this orbit, then then actually Q belongs to R hat I naught G naught of P. So it actually lies in the horizontal. Now the proof corresponds to taking two sets. So we first take D1 is such that if X belongs to D1, then mu tilde X I naught J naught is delta at X. So remember, with the bar is the measure in the real lines, with the tilde is the measure on the manifold itself. So this will be a little bit more geometric than before, so we are really arguing over there. So, and again, this is a set of full measure, and actually is more not so much about being delta than about this guy being well defined. Okay, we know it has to be delta because it's in the Q minus, so it's outside of the Q. And then I will define D2, and D will be the intersection of D1 and D2. So take K, mu of K larger than 1/2. Here 1/2 is important. We will see in a second why. It's a very cute argument actually. So, okay, we take this set of measure K compact and such that Y into mu tilde Y is continuous. So it's losing set of continuity of these guys. Again, and continuity means, so on this side you just put radon measures. So, and yeah, maybe it's better to actually to put the bar, but then I can use the parametrization and go from the bar to the tilde without any problem. So with slight abuse of notation, I just claim these guys are continuous. Okay, so I have this continuity. And then I will take D2, which actually will be inside D1, will be the set of points Z such that 1 over n, I could do the integral, but let me do the summing. It's really no difference. Up to n minus 1. How do I call them? Et. So EKT. T is the T I described before. Applied to Z. And actually, characteristic of K of this point and again I have ergodicity, so I have the luxury of doing what I'm going to do. So I just assume this. And this is a set of full measure. That's what ergodic theorem tells me. So okay. So once I have this, so D is equal to D2. And now I have to prove what the guy is asking. So I take. Is K? Yeah, it's maybe, but maybe it's better since I'm using the K here. Let's call it IT. So yeah, so this is e to the I t1, e to the it2, e to the it10, 0, 0. And again, I probably is not, let's call it L. Because then we have the ij's, and of course my E and my L are the same, but I don't have enough letters. There's already not many letters in the alphabet, and on top of it I write all of them the same, so this is really hard, pero bueno, what to do. Okay, so I have this guy, and now we go to the picture and see what the picture is telling us, and we just write down what the picture is telling us to do. So we take P, we take Q, P and Q are in D, which is in D1, so these conditional measures are well defined and are atoms. So I have an atom here and an atom there. And I have also that bores are in D1, so they both visit with reasonable amount of frequency the set K. And they are like in the picture because Q belongs to the R of P, so they are really related the way I'm drawing it. Now, I will take iterates AKIT, where this KI will be chosen in a second in a reasonable way, will be a subsequence, in such a way that this picture goes to infinity. So I will take, in particular, AKIT of P going to some p infinity, then I will have, that just follow from the picture, that this is at the same time converging to some q infinity, and in such a way that if this distance is d, then this distance is d in these parameters along this hij infinity. So to be more precise, if this is p hat and I have q is hi naught j naught s of p hat, then q infinity is hi naught g naught s of p infinity. Okay, and this just follows from the fact that the guy is contracting this direction and is isometric on this vertical direction, so I get this for free. Whatever subsequence I take going to infinity, so that this goes to p infinity, this will have to go to q infinity with this relation. So since I want to, okay, this is s, since I want to show that s is 0, proving it here being 0 or proving it here being 0 will be the same. And I'm going to prove there that s has to be 0. Now, essentially, the proof has to be done because I have, well, I want the following to hold true. So when I do this is the same as the I naught j naught. Okay, this is delta in ak t of p, which is the same as aki t star of mu tilde p, I naught j naught. Same thing happens for the q, aki t star mu tilde q, I naught j naught is delta in aki t of q, which is this mu tilde aki t of q. Okay, now as soon as I can pick aki t of p belonging to k and aki t of q belonging to k, so the first will tell me that this goes to mu tilde of p infinity, which is the same as delta at p infinity, because continuity k is inside d1 and blah blah blah. Yeah, maybe I should d1. And the second implication tells me that this guy is delta at q infinity. And the last implication tells me that in both guys, since p infinity is h I naught g naught or q infinity, oops, s of p infinity, this implies that mu tilde p infinity I naught g naught has to be the same up to a multiple, all are delta, so that really doesn't matter, I naught g naught. So they have to be essentially the same, and so I forgot here the I naught j naught. So this implies that p infinity has to be equal to q infinity, and hence s equals to 0, and the measure lies where it has to lie. So the big question is how to get this sequence belonging to k simultaneously. So having one guy belonging to k is just standard ergodicity, so I didn't even need to argue. Okay? Actually, it's equivalent to ergodicity, the fact that for almost every point, for every positive set, I have such a sequence. Now, the ergodic theorem tells me more than that, tells me the frequency of visit to these guys, and then you just define a of p equals to the case or the else in Z, the natural, such that A, L, P of P belonging to K. A of Q is the same guy, but for Q. And then finally, you know that, so this statement is equivalent to 1 over n A of P intersected with 0 n goes to mu of K, which is larger than 1/2, and the same with the Q. Goes to the same number, which is still larger than 1/2, and so A of P inter A of Q is non-empty and actually is infinity, which is all I care. So it has positive density, but I just care if being infinity, because then I can take Ki here. Belonging to this intersection, a sequence, any sequence there, and I take a subsequence making it conversion to some limit. I use compactness there, this compactness of K, so even if this global space is not compact, K is compact, so there is no problem of taking subsequence, and I'm done. So, and that's the core of the argument is these integrals. Okay.
So I have a question.
Yes.
So from the first two, how do you show that the intersection has to be infinite?
Oh, it's because you show. So this, even though these are not measures, once you know this limit exists, they work like measures. They really work like measures. You can show that AP, so this Banach density for set, once you really know this guy, so this guy 1 over n, I don't know, the lim sub, the lim inf, whichever, I guess lim sub is good enough. Probably it's even true with lim inf. Yeah, I think lim inf will also be true. This will be larger than 2 mu of k minus 1, I guess, which is positive. And then if this were finite, this will stop. So it will have a maximum, and then this has to be 0. So again, this Banach density is not a measure on subset of the natural numbers, but it's the closest you will have ever to such a guy. And it will do the job most of the time. And this is the standard game. So you write this guy, intersection AQ, intersection 0n, is like the union intersected 0n. How do you do it? No, it's okay. It's 0n minus the complement of this union the complement of this, I guess. And then the cardinality of this, it will be equal, since one is contained in the other, it will be equal to n minus the cardinality of this. And since I want this an inequality, I hope I'm doing it correctly. So I will get an upper bound for this guy. And the upper bound is by splitting the sets into 2 different sets. So this is then less than or equal, n minus 0n minus A of Q complement intersected 0 n. And then this guy, since this limit is really a limit, this is like n mu of k minus n, and this is or n minus n mu of k, and this is also like n minus n mu of k. So in a sense that when I divide by n, this goes to 0. So then I just take a common n everywhere, and I'm getting 1 minus mu of k, well, 1 minus mu of k minus 1 minus mu of k, and this is what is giving me the n times 2 mu of k minus 1. And you bring the n to the other side, and you get the bound, and you get the lim rather than the lim sub. But again, doesn't really matter. So a lim sub will do. Okay. So this settles this part of the game. Yeah, maybe before. Let me try just to finish with the factor group, and then I discuss a little bit more about this lemma, about this picture especially. So we saw essentially the same game give us the corollary. That was that mu tilde q, mu tilde g p is mu tilde pp for p mu almost every p. Actually, it was mu tilde, the measure. And now it comes to the time that we have actually to do something about it. So remember, what is the measure mu tilde? So this is a measure on G mod P, not on G mod P, I'm sorry. It's a measure on G times X mod gamma, where we have this whatever action, and it's the projection essentially of the infinite measure, which is the graph of our pi functions. Okay, so we have pi from G into X, which is P invariant, meaning pi of Pg equals to pi of G for every P in P, and actually it's also true for the Q. That's how we define Q. And when I do pi of G gamma, it was the gamma star, or gamma applied to the pi of X, which is the gamma action on X. So, and then the measure mu tilde was of a set A was the integral of, or better to do how we integrate functions, phi of gx is the integral of phi on g pi of g dg. Here it is, mu tilde. So that's how you define it on g times x, and then you descend it on the fundamental, so you restrict it to the fundamental domain and project it to this space. And the second property tells me that it doesn't matter the fundamental domain you choose. Okay. Now this is telling us about the P invariance, and as we know, this is even Q invariant. But now we know a little bit more, which is these conditional measures agree for almost every p. So now this implies there exists R contained in G times X mu tilde of R complement being 0. So it's a set of full measure for mu tilde. Actually, it's a lift of the guy in the G mod gamma, so, but I prefer to denote it here, such that Q R intersected G of P is equal to Q intersected by G of P for every P in R. R also will be gamma invariant, so gamma R times gamma actually, then move it in this way. So every gamma. So I'm abusing again the language here, GP. So let me be a little bit specific here. So P is a G naught X naught, and GP then is G X naught. So it's G times this X naught. Okay, so it's the natural action of G on the points on this space. While when I multiply in the other direction is the other action which I use to write down the quotient. Okay, so P times gamma is G naught X naught gamma, which is G naught gamma gamma inverse X naught. Yeah, and this is a G naught and X, of course. Okay. Now, what is this set? R essentially is this set here. So this is true for almost every P. Then I have to do one slight modification of the set R, so I have to ask a little bit more, but essentially is all the P's where this is true. This is a set of full measure, and that's all we care. So let me see if I have to say to do something else. Just 1 second. Do I want P to be in the support or I don't care? Okay, let's just go and see what happened. Minus P such that, so maybe if you want, let me do it. This epsilon detail. So R hat containing G times X mod gamma, so that P hat in R hat implies mu tilde G is equal actually Q hat Q. Also included in R hat is the fact that this is a well-defined measure and this is a well-defined measure, and they coincide up to a constant. And then I take R intersected GP. So R actually is okay. Now I need to a letter eta inverse of R hat, where eta is from G times X into this quotient. So I just take the lift, then automatically this gives me this automatically, because I'm just taking it up. The fact that this R hat has full measure, so tells me that for this other, which I also call it mu tilde, that the complement will have zero measure, again because on the fundamental domain it does it. The shop. So, and now finally I take R intersected this orbit. Now the observation here is that the support, so this implies that the support of mu tilde p hat G is contained in QP hat, because if these two measures coincide up to a multiple, even if they were just absolutely continuous, it will be, or equivalent, it will be enough. So the support of this measure has to be here, inside the other guy. So this guy is contained in the support, or is a set of full measure. Yeah, maybe that's why I wanted a little bit more, but still. So mu tilde p hat or pg. Okay, maybe let me denote yeah, I should have done it before. Okay, let me abuse a little bit of the language and then we discuss it. Mu tilde GP of R complement intersected P. There is no need to intersect because this is already supported here, but this is 0. And then this implies that mu tilde GP of, when I put the Q, this is also 0, because these two measures are essentially the same. And this implies that R intersect GP is contained, complement, is contained in the support of mu tilde QP, which is contained in QP. Okay. Now, what's the above use of language I did is essentially the following. I took P hat, and here I'm taking P upstairs. So I'm using this same map, eta, from the G orbit of P into the G orbit of P hat, just restricted to the orbit. I'm just using this projection from the universal covering to this guy. And this projection is actually one-to-one, unless something strange happens, which is that the stabilizer, the gamma stabilizer of the X is not trivial, which essentially will happen with zero measure. So I can forget about this. So this gives me a complete identification between these two guys. And so when I take the measure down, I can bring it up and then discuss this phenomenon here. And since the R is the preimage, complete preimage of the R hat, then there is no problem between putting the hat here or not putting the hat here when I do this identification. So then these lifted measures mu tilde at P are again the same as these guys, and then the argument goes through. Okay. And once I have this lemma, this lemma, then I'm done. Because now I take R mod Q. Okay, wait a second. So, no, that's not what I wanted to do. Let me go again. So I have my set R contained in G times X is a set of full measure on the product. So it sits on the graph. Okay, I will leave one argument outside. I should have done it, but I will do it probably later. It's a completely ergodic theoretic argument, which I have been bypassing it forever. I always told you that I was not doing that, but I think now it's probably important to have it, which is I can assume that Q times R is equal to Q, equals to R mod 0. So I want the set R to be Q invariant. So again, if I want to do it for finitely many Qs, then it's just a matter of integration, of intersection, but the group Q has uncountably many elements, so then this amounts to some explanation. But it's an argument in Fubini, essentially. So we will discuss Fubini for that. Then I will have the R is essentially Q invariant, and then I project R into the G mod Q, projecting into the first coordinate. So I take psi from G times X into Q mod G.
So did you mean that you can take R such that QR equals R
mod 0? Yeah, exactly. I can assume in this lemma that this is also true.
Okay.
And the way I can do it is because I can actually do it for the R hat. And once I can do it for the R hat, I will have it for the R. And I still have to explain why I can have it for the R hat. And the point is that R being a set of mu tilde, of full mu tilde measure, plus the fact that plus the fact that mu tilde is Q invariant is giving me that I can change the R hat before by a new R hat doing also this property. Again, if Q were at most countable, you just would take intersection of Qn R hat in here. And this will be the new R hat. And we'll do whatever you want. It's a subset of R hat, so whatever it did before, this does it now. But now this, you would like to do that, and this is uncountable. And you have to argue that this still has full measure. And this is more a Fubini type of statement. It's not. We are already out of time. Boy. Okay. Okay, give me 1 minute, so because with this we finish finally the normal subgroup theorem. So, okay, so what I want to show now is that this transformation pi, pi, which is well defined because we have the Q invariance, so the original pi was Q invariant as well, so that this is one-to-one on R, or actually R tilde, which is this projection sign of R from here. And well, the argument is that if I take x1, x2 in psi of R, this guy has full measure because of the R has full measure, so, and the R is Lebesgue measure on the first coordinate, so you project to full Lebesgue measure in the first coordinate, so you project to full Lebesgue measure on this G mod Q. So this is a fully defined guy, so lambda is 1, or of the complement is 0 if you want. It's finite measure, so it's not a problem. Now if I take 2 points there, in this guy, and we assume pi of x1 equals to pi of x2, then I know they are in the same G orbit, because every pair of guys are in the same G orbit here. But I also claim, maybe let's call it Z. But I also know that then they will have to be in the same Q orbit, because that's the whole point of the R hat, or of the set R. So this implies that C2 is G times Z1 . Oh boy, come on. And this guy is X. So they I want to finish today. Maybe I cannot do it. Okay, let me just do epsilon careful. So the fact that they are here, this implies that C1 equals to Q times G1, C2 equals to Q times G2, where G1, G2 belongs to R. Okay. And I have that then, by definition of this, pi of G1 equals to pi of G2, because the pi is constant along Q orbit, so, and I can have it well defined on any coset here. And now, so this is still X. This implies that I have the pair G1X and G2X both belonging into R. And now the precise definition of main property of R in the lemma tell us that G1 has to be equals to some Q times G2 for some Q in Q. Because whenever they are in the same G orbit, they are because the second variable is the same, then they have to be in the same Q orbit, which is exactly what I said. And then this implies that C1 is equal to C2. Because if I have that equality there, then I have that these two elements are the same. And then we are done. Okay, so this finished the factor theorem and also the time. So probably we will discuss later on Friday the Fubini, how this Fubini, and this is in general for any group with a hard measure, how you go from a, when you have an action of such a group preserving a measure, and you have a full measure set, how can you swap from a full measure set to a full measure set which is fully saturated by elements of Q. And well, we will see this picture again later as well. Okay, thank you. Okay, so let's go. So one comment on one thing we did last time. Well, I have two comments, one more serious than the other, so let's start with the serious and less serious. So we had this set R, full measure. Actually, it really doesn't make any difference if we consider it here or in the quotient, so it's same considerations will go through. And essentially we want to change it with a set which is Q saturated. So we want to change R to a Q saturated set. Okay? And what's the main property of R? The main property of R is the fact that R intersected, actually, the main property was that for P in R, the conditional measure of P along the G orbit was the same as the conditional measure along the Q orbit, up to a multiple, of course. And indeed, out of it, we essentially had that R intersected the P orbit of G is R intersected the Q orbit of P. Okay, so that was the main property we wanted, but now we wanted it to also happen for Q saturated sets. So in a Q saturated fashion. So then you just go and define R hat, R tilde, as all the sets point Q, maybe Q is not a good name, GxX, such that for mu tilde xq almost every y, this happens. And this is just y is in R. Okay, so that, and now essentially you don't care so much about R having this property or that property. Of course, it has to be something related with Q. But the main importance here is that the measure of R tilde, so if R has full measure, then R tilde still will have full measure. And the second important property is that now naturally R tilde is Q saturated. Okay? Because this property is a Q saturated property naturally. Because this measure is independent of the point in the Q orbit. So
Q saturated, you mean R tilde Q equals R tilde?
Yes, exactly. Yeah. Of course, again, there is a slight abuse of language here. So if you want to do it with all the details and care, you have to even go and do one more step, because this measure is only defined on a set of full measure. But you can extend it naturally and assume it is defined on a Q-saturated set. Okay, because you know that if y is in the Q orbit of x, then u tilde x Q is yq. Okay, as soon as these belong to whatever set of full measure where the both measures make sense. Okay, but now once you know that this is true, you can move first the R naught to a second guy R naught tilde, and in this R naught tilde you define the measure, so in a Q-saturated fashion, and you just define by this formula. So any of the guys, the closest or whatever. So this is really not important. And so once you have this definition, then this measure is defined on a Q-saturated set, and then this is a fully Q-saturated condition. Okay, because this measure now is completely independent of the business. And even more, if you want to be 100% detailed, so we only define up to this notion, but that's okay. You just look at these measures as elements in the project device guy, and then you do extension in the project device guy, but still the notion of almost everywhere is very well defined, and it's still a Q-saturated. And now this guy is Q-saturated, and every point there essentially will have this property naturally, because this didn't change at all. Okay, and the other as well. So that's how you typically argue when you have to do this business. So you always go to a guy which is stable in a sense of this property. So that's a very standard way of arguing in ergodic theory, and it's a typical way of going on. Okay, so that's one thing I wanted to comment. Now the second thing I wanted to comment is going back to our picture, which is a very important picture in the theory. So we had this contracting direction and this isometric direction. Okay, and actually this isometric direction was a contracting. Let me maybe do it this way. I could make it contracting if I wanted. Okay, and I have this measure, conditional measure mu r. So this is the group R associated with the roots ij that I was talking about. This is the I naught j naught direction. This is the complementary guys, all the remaining guys. And assuming some trivialization charts and whatever, what was crucial in the argument was the fact that this measure mu r is equivalent, because I didn't need more than equivalence in the notion of equivalence by measures. So equivalent as measures, i.e. same zero sets to mu, these are the point x, mu r hat I naught g naught x times mu I naught g naught on x. So that this ambient measure was essentially the product of the measure here and the measure here. So that was what was in the core of everything. So this is, so in general, in dynamics, this is not the case. Okay, so this is a very important fact and problem in dynamics, and it's a very important source of rigidity, the fact that you may have this property. So the typical example, one of the first examples actually, is Katok's example. So it's just an example where this type of picture completely fails. Okay, and let me just draw the picture of what he does. Is a measure on the square. It's actually the circle times the interval, but you can move it to the square without a problem. You have a vertical foliation. Which is very explicit, so I can write formulas later. So each leaf is real analytic actually. And you have a set A with leg of A being 1. So this is 0, 1, 0, 1. Each of these guys is the leaf through a point P. But Lebesgue one-dimensional, or the leaf P of f of P is 0 for every P. And moreover, actually it's for every P. And moreover, if you take these conditional measures, f P, this is P almost everywhere. Okay, so this second statement is telling me that this set A actually so the cardinality of this is 1 for almost every P. So you have just one point, so this set A, which is full Lebesgue measure, still is a graph. It's a graph with respect to this. I call it the vertical foliation. It's not fully vertical, it has some movement, of course. So each individual manifold is real analytic, but when you move from point to point, its variation is very ugly. Okay, so in particular, this completely rules out a Fubini property for this foliation. So imagine that this foliation had some Lipschitz continuous foliation charts, then you can straighten them up into making them fully vertical. And since they are Lipschitz, Lebesgue measure will map to Lebesgue measure up to set of 0 measure. And then you will have that this set A, which has full measure, will be full measure here. And Fubini tells me that a set of full measure actually is even Cavalieri principle. If the set has full measure, then for almost every vertical line, you need to have full measure. Okay? But these curves intersect in a point, so you cannot have full Lebesgue measure if you are intersecting each other.
So isn't it the case that each leaf starts at 0, 0 and ends at 1?
Yeah, actually they go all the way up to there, but yeah, you're right. But you can do several sort of different type of examples, and it really doesn't need to do that. So you can actually concentrate here.
There's a question.
Yes. Oh, good. Yes, the example is purely dynamical. Then there are other examples. There is Shub-Wilkinson example, which is more related to non-zero exponents. Here is more related to singularity of measures, maximizing entropy or of the conjugancy. So let me just write down easily the example, then we can discuss, or maybe not discuss, you can go and read why it satisfies all the properties that we care. So you do the following. Take a family of maps from the circle to the circle. Actually, ft of x is 2x plus, and then you just put something nice. So something like t sine of x, or t over 100, so that we make sure this is small. So probably we don't need the 100, but it really doesn't matter in the interval t in the interval 0, 1. Okay, so these are expanding maps for each parameter t. And as I said, it's actually the cylinder, it's not the circle. What we do? And you can look at you can think on two different ways. You can see in the product system, f of tx equals to t ft of x on this cylinder, where each circle goes into itself. Or you just don't need to really actually think on this system. Now the point is that this system has what is called a center foliation. So you will have the circles, which is the vertical foliation here. Actually, this vertical will become horizontal in the picture, but anyway. So which is this expanding foliation, and then you have a central foliation associated with this guy. Now, what are these center leaves? They are parameterized by the following. So you have, for every t in 0, 1, you have a map ht from the circle to the circle, which goes ht compose ft is equal to f naught compose h t. So it's the conjugancy to the linear. And if I wrote the equation correctly, then I will have that f of t ht of x is the same as t f of htx, ft of htx, and then I wrote it incorrectly, so it should have been this then, and then this is t ht of f of x. Okay, so you see that the leaf, so this curve t, the graph of ht, when I apply f through x, it goes into the graph of f of x through h. Okay, so it permutes this graph. And it's a family of graphs, so it's clearly a foliation, a partition, because in the first coordinate you are doing good, in the t coordinate you are doing good. And h of t is a homeo for every t. Now, the dependence of t on ht. This can be done either explicitly, you go to the formula to the ht, which can be computed very explicitly, option number one. Option number two, you use center manifold theorem. This has eigenvalue 0 in this first direction, and then you will have that these curves are real analytic. So just a matter of radius of convergence. It's really not too hard. So this is the foliation. Is this foliation? The foliations into these graphs. And now the point is that if you take Lebesgue measure for this circle, or for any circle, actually, maybe let me be more explicit. So for every t, you have a measure mu sub t on the circle. Mu sub t is actually some phi sub t dt, dx, sorry, phi sub t of x dx. So it's equivalent where phi sub t is again real analytic and uniform bounds, everything beautiful. But when you do this holonomy along this sliding by the t, so this is invariant by the ft. But when you apply the ht, this will become singular. Okay? And even more, now is where really comes the how you get the set of full measure. I have this measure, which is mu sub t dt. So mu of a is the integral of mu sub t of a. Here I'm slightly abusing language by mu sub t is a measure on the circle. Now it's a measure on the circle through t. And then I intersect this with this guy, dt. And this is a measure on the whole square, which is equivalent to Lebesgue, because all these measures were equivalent to Lebesgue. And actually, what is the Radon-Nikodym derivative is this phi sub t dx dt dx. So that's actually the measure essentially. Okay, so this measure is real analytic in the t variable. I'm sorry, is real analytic in the x variable. It is continuing in the t variable, and I think it's still, yeah, it is real analytic in the t variable as well. It's not really important for our purposes. That needs a proof, but it is. Okay, nothing that is of importance for us, but that's the measure. And this measure mu is invariant by capital F. And now what is the set A appearing up there? Is the set of regular points for Birkhoff for the capital F with respect to this measure mu. Okay, so the set A is equal to of the set points x, or tx rather, 0, 1 times the circle, such that sum from k equal to 0 up to n minus 1, 1 over n phi on n u xt tx, this limit as n goes to infinity, this is this limit exists. For every function u is 0. Okay, the measure mu is not ergodic, so I cannot ask to this limit to have whatever value. Actually, we know what is the value. I claim it exists, and actually I can be a little bit more explicit. This will be the integral, let me see. So this is u of t fn x. So u of tx d mu t of x. And this is for every u. This is okay. For every u in C0 from interval 0, 1 times s. Okay, I know the decomposition into ergodic components of the measure mu because I build it so that I have the decomposition into ergodic components. So each ergodic component is one of these circles, and the measure on this ergodic component is this mu sub t that appeared there. So Birkhoff tells me that mu of A equals to 1. That's the first thing Birkhoff tells me. The second thing that Birkhoff tells me is that the definition tells me that this Lebesgue set of A is equal to 1 because mu and Lebesgue are equivalent measures. And now the claim is that A intersected with the leaf through a point P or Tx is less than 1 for every T and X. Okay, and the proof, let me see if it works. I may fail. Okay, and then we will have to go to the paper at some point to read it. So imagine it's not. So take T and X, and assuming you have 2 points, so I have T1, X1 in A, T2, X2 in A, both in graph through the point X of H sub T. Okay, so this leaf, so the point X, we know it is all the points S, H, S of X, such that S is in G1. So these are the leaf. So what do I know then? I know that though both points are in this place, so it means that there exists an X such that ht1 of X equals to H wait a second, equals to X1, ht2 of X equals to X2. And for these values of T1, T2. So that's what I know. Okay, so far so good. Now, if I do ht1 compose ht2 inverse, this guy, if I wrote things correctly, which I probably didn't, if not I have to do the other way around, when I conjugate, I need to do this inverse here, with ft2, this is ht2 compose ht1 inverse compose ft1. So the map ft1 is conjugated to the map ft2 by this conjugancy there. Now this conjugancy is mapping x1 into x2. Okay, I guess it's maybe the inverse of ht1. This guy should be sending x1 to x2. Or maybe, am I doing it right or am I doing it wrong? Yeah, okay, good. I take x1, I apply the inverse, it brings me to x. I apply htx2 and it brings me to. Okay, so h2 t2 compose ht1 inverse of x1 is equal to x2. Good. Very good. Now, why this is impossible? That's the question. Okay, and the reason is, what is this guy doing? Okay. So what I know is that the sum of u t1 ft1k of x1 k equals to 0 up to n minus 1 over n. This is conversion to the integral of u t1 z d mu t1 for every continuous function u. Okay, now let me call this guy capital H. Capital H, I said. And actually, probably I need to do this for ft2. But anyway, let me write down here ft2k compose H equals to H compose ft1 to the power k. So let me put here the H inverse here and plug this in there. Okay, so then what I get? I get 1 over n sum from k equals to 0 up to n minus 1 u of t1 f, h of ft2 k of x2, and there's an inverse here. This is convergent to this guy. For every continuous function u. Very good. So in particular, I want to convince you that this implies that 1 over n sum from k equals to 0 up to n minus 1 of v for every continuous v. And the reason for that is just do it for the function u of t1 z being v of and no dependence on the variable t. Okay, so you plug this function down here and you get exactly the second formula. Now this implies, on the other hand, I know, again by definition of A, that this has to go again, it's just a function that is independent of the variable t, so I can still apply it for the functions which are independent of the variable t. This has to go to the integral of b d mu t2 of c. So this implies that when I do h star mu t1, I get mu t2. So all this was just to prove that. But mu t1 and mu t2, they are both equivalent to Lebesgue measure. This implies that h star is equivalent to Lebesgue measure. Now here is the final punch, is a lemma that says that if h star Lebesgue is absolutely continuous with respect to Lebesgue, which would be the case up here, then ft1 prime at 0 has to be the same as ft2 prime at 0. And who is 0? 0 is not just whatever point you want in the life, even though 0 is always a good guy. 0 is the fixed point for this guy. Okay, and now you go and compute the derivative. ft1 prime at 0 or ft prime at 0 is 2 plus t over 100. So it's injective on t, so there is no way it attains the same value. Derivative of sine is minus cosine. No, it's cosine, yeah. So then it's correct. Even though to have it well defined, there should be a 2 pi there. Still doesn't matter. So then this is impossible, which implies that I cannot have 2 points in the same fiber. Okay, so that's the famous Katok paradoxical example, which if you want to read, there is this paper by Milnor about Fubini foiled, which make this description maybe with some more details or different. I'm not sure. I think I read it once, or at least I saw it, but yeah, I cannot recall it. But yeah, that's the example, and this is an example where this previous picture completely fails. So I have Lebesgue measure. I have this is atomic. This guy, you can prove that is actually Lebesgue because it's conditionals along the circles, which are Lebesgue. But these other are atomic, and the measure is not lying on a circle. It's Lebesgue. So this completely fails. Of course, in this case, this direction is isometric, while the other is expanding. You can do arguments with expanding versus contracting. There are examples where you have this guy is contracting and this guy is expanding. And so these are the Shub-Wilkinson examples where you still have atomic on this direction, but the ambient measure is Lebesgue. So you still don't get anything. So the question is how to get this property. So we saw an argument which guarantees this property. This argument used the isometric property along this direction. And now one can start thinking of what's wrong here then, because, or there or here, because here you also have isometric on this direction. So even though the curves are not fully horizontal, so it's not really the first variable, is the first variable with the second variable, so the tangent vector is something like that. Still, the tangent vector will have uniform bounds when you iterate it by f. Okay, so it's not growing at all. So you can pretend it's an isometry and try to do the same argument.
Before we move on,
yes.
You said in this Rodon-Equivalent derivative phi tx that it's analytic in t as well.
Yeah.
So does that mean that the holonomies analytic? Because the full
It means that no, it just means no. The holonomy is Helder and not better than Helder. So here is an important thing about these HT functions. So when you fix t, so actually it was here. This map here is, which is the capital H, is actually holonomy from the circle through T1 to the circle through T2.
Yes.
Okay? Now, this holonomy is Helder, as any conjugancy is in general, is not better than Helder, and shouldn't be better than Helder, and that's that lemma over there. If it is a little bit better than Helder, then it's actually very smooth, reanalytic, wonderful. I can evaluate it at 0 and get a contradiction. So the holonomy is not. Now, if I fix the point x and look how the conjugancy for a fixed value of x depends on parameter, this is a reanalytic function. Now, this function phi appearing here is about the dynamics f, is not about the conjugancy. And so is reanalytic on the parameter t, because in dynamics, dependence with respect to parameters is always beautiful. Is reanalytic with respect to x, that's for a different reason, but is still a beautiful differentiability there. Is some sort of Fubini contraction mark principle actually happening there. Okay, but it's again, it has nothing to do with the A, and actually H is singular with respect to these measures. That's the whole point here. Okay. Maybe let me draw a picture for completeness, which is why if H is so this implies, so the proof of this is the following. Let me see if I can do it. Yeah, it's actually not so trivial. Ah, it's okay. It is actually trivial. Here is the proof. Okay, again, the measures here are not Lebesgue, but they are equivalent to Lebesgue with a continuous Radon-Nikodym derivative bound away from 0 and from 1. So it's really, I can pretend, since H after all is just continuous, well, it's actually better because it does this, but let me even imagine these are dx. It really doesn't affect the argument. Now you have 0 here, you have 0 here. Okay, now a matter of dynamics is telling me that if I take a very tiny interval, actually I have a sequence epsilon n going to 0, and the speed with which epsilon n goes to 0 is epsilon n1, is pretty much like fn prime at 0, t1 prime at 0 to the minus n. So I have these sequences here, going to 0, so that fn of, let me just even put f0 epsilon n1 is the interval 1/2 0, say. Just some magnified guys. Okay, so I go microscopic here, I iterate n times, and I get a uniform size. The same with the T2. So I can put now an I here everywhere, and you have this. Now, the dynamics will have to send this interval to that interval. Okay, because this epsilon ni is nothing but fn ti 0, fn ti inverse of, say, 1/2 or 1 or 100, whatever. So I take the branch of inverse going to 0, and I just keep on taking always the branch of inverse, and that's the epsilon ni. And you have that they really behave like the derivative at 0. And now dynamics, so the conjugancy H have to send the epsilon ni to the epsilon n2. Okay, so I have this microscopic guy going to this microscopic guy. Okay, now the mu-T1 measure of this guy is up to some number epsilon n1. Okay, so it's uniformly bounded. Actually, is C1n, where C1n is uniformly bounded away from 0. And the same with the mu-T2. Actually, as always, I can put i's, and then no need to write it twice. But H being sending this measure to this measure, it tells me that the measure of this guy is the same with respect to the 1 and the 2, which means that these numbers are the same. But this was an exponentially decreasing sequence. This is another exponentially decreasing sequence. These are constant bound away from 0 and infinity. And so if they are the same, it's because these lambda 1, lambda 2 have to coincide. Because if not, you will escape to infinity or go to 0. So this tells you that lambda 1 is lambda 2. That's it. So this is the lemma, and now that's the complete. That's all the details for this proof. Okay. Then maybe I go back to what I was trying to discuss, even with 0 minutes. I think it's really worth every second. So it's a beautiful example. It's a very important example, and it really goes pretty well in the course. So it's really no time wasted at all. But still, okay. So the point is, here you have this product structure. Okay. Now I want to bring back this entropy word, this entropy game that appeared when we do times 2 times 3 or multiplication by matrix A and matrix B, of which the only thing we cared was the fact that entropy of F being 0 if and only if the conditional measure along the unstable for P is delta at P. So that was the sort of mantra we used there, black box that we used there. Okay, so which is actually true, and that's Ledrappier-Young. Is that H mu F is Lyapunov of exponents times, so positive, times dimension of mu u. Okay, and again, that's some sort of black box that I should make it more explicit, and I want to make it more explicit actually, because that's the whole game here, is in being able to make this more explicit. So in the case that the entropy is 0, you get a 0 here. The positive diagonal exponents are positive numbers, so dimension has to be 0. And then in this case, you have a little bit more. It's not just 0 dimension, it's an atom. Okay? But that's because it's 0 dimension implies an atom. Dynamics is very nice to prove that. In general, if it is positive dimension, then you have positive entropy. Now, how this positive dimension behaves is not obvious at all. Now, when all the exponents are equal, then you can remove the quotation mark, and you actually will have this game. Now, when the Lyapunov of exponents are different, and that's exactly what these arrows here mean, this is contracting, well, this, you should think taking F inverse after all, where this exponent, say, is larger than this exponent here, then still is true, and the formula reads, we still have to be quotation because you have to understand what the formula is telling you. The formula is beautiful, but you can be can be very deceptive. So is chi1 dimension, dimension of mu1 plus chi2 dimension of mu2. Okay, and here I'm just calling it the W1 direction, the W2 direction. And then in this direction you multiply like e to the chi2, in this direction you multiply like e to the chi1, and this is what the formula is. And the second part of the formula tells you that the mu12 dimension is dimension of this plus this. Okay. Now, what are these dimensions I'm talking about here is even more complicated than what was the dimensions we were talking before. Okay, so it's not anything trivial. What this is not telling you is that this measure mu12 is equivalent. So this is not telling you that. And it will never tell you that. This is 99.9% of the time false. It's only true when there is some rigidity happening. And still this formula holds that the other implication is true. If you knew for whatever reason that you had that this measure on this two-dimensional picture is the product of the two one-dimensional measures, then you could prove this formula much, much faster than what Ledrappier-Young did. Okay, the good point is that this formula can be proved in all situations, if understood correctly. And I will discuss a little bit more what does it mean to understand it correctly in next Monday. So I will explain what is dimension of mu1, what is dimension of mu2, what is mu1 and mu2 actually here, which is not exactly conditional measures. Well, you want them, you don't want them, so whatever it is. So I will explain what it means and how really you relate it with this and how much you can prove in the general situation of this formula in settings similar to what we were doing in this Margulis normal subgroup theorem. Okay, and what you will be able to prove is actually, again, in these sort of settings of Margulis normal subgroup theorem, that the entropy along the two-dimensional picture is the sum of the entropy along the horizontal plus the entropy along the vertical. This doesn't give you the picture for the measures, but it gives you the picture for the entropies, which again is much stronger than what Ledrappier-Young is giving you because you have more assumptions. Okay, and with this, pretty much one can do everything that is It is actually, it has a very important component of Abrahamov-Rockley. It's actually a situation, we are going to discuss exactly that. So even in a more philosophical way, this Ledrappier-Young is some sort of Abrahamov-Rockley formula. And what I'm going to discuss here is when you have some sort of fibered system, so it's not a product system, but it behaves like a product, meaning that you can look at the system as having a quotient and the fibers over this quotient, or you can project to the fibers and have the horizontals as to the quotient. So it's like a product would do. So you can project in both directions and think that you have as factors this guy or you have as factor that guy. Okay? And then you can reverse the roles. And the point is that when you can reverse the roles, then you will have a nice addition formula for the entropy, which is better than what Ledrappier-Young is giving you. But this requires a lot of work. So I'm not going to do any of the details to guarantee whatever formula there, but I want you to know that some things happen in there. Okay, that's it. Thanks. See you.